Good evening, students, and welcome to today's session. So we have been discussing about Newton's laws of motion, and we've seen various things like constraint relations, application of pseudo force, etc., and the application of free body diagram concept. So these are some of the things that we've learned about Newton's laws of motion, and we've tackled the H.C. Verma problem set so far. Now today we will learn the next concept related to Newton's laws of motion, and that is the concept of frictional force. So it's a separate chapter in your textbook or in your module, but basically it is a continuation of the concept of Newton's laws of motion and application of Newton's second law, and the relation between force and acceleration or force and rate of change of momentum, and that is the concept of frictional force. So we will start with the concept of friction today. So though it is basically a new chapter for us, but it is a continuation of the same concept set that we've been learning, which is Newton's laws of motion and applications of Newton's second law with the free body diagram method. But now we will incorporate in our free body diagram or in our mechanical systems the additional force of friction. So let us see by definition what friction is. So friction is also a type of contact force. Okay, but unlike normal reaction, friction does not act perpendicular to the plane of contact. Rather, friction acts along the plane of contact. So when two rough surfaces are rubbing against each other because of a tendency to slip against each other. So because of the roughness of the surfaces, there's a force that acts along the surface that is tangential to the surface, and that force is called friction, and it tends to oppose the slipping. Okay, so it's a type of contact force that acts between rough surfaces in such a way that it opposes slipping. It has a tendency to oppose the slipping. Okay. So friction is a contact force, okay, that acts tangentially. So tangentially means parallelly. It's parallel to the plane of contact between two surfaces such that it opposes the slipping between the two surfaces, opposes slipping or sliding, okay, between the two surfaces. So friction generally comes into play when the surfaces are rough. Generally speaking, friction acts in the case of rough surfaces as opposed to smooth surfaces or as opposed to polished surfaces. So for example, if we have a situation like this where we have a rough surface like a rough concrete surface, which is not smoothened at the top or it's not polished at the top. So this is a rough surface. A good example of such a rough surface, as I told you, is a concrete surface. Okay. And we have a block. For example, it is a stone block. It is made of stone. So this type of surface, stone versus concrete, will have a high degree of friction. So we might observe that in spite of applying some external force, okay, what is happening is that the block is remaining at rest. We might be applying some external force trying to push the block, but in spite of applying the force, we see that the block remains at rest. Okay. So a horizontal external force okay, is applied such that the block should have a tendency to move, but we are observing that finally it's not moving. It's remaining at rest in equilibrium. So it should have a tendency to slip along the horizontal surface. However, due to friction, okay, between the so-called rough surface and the block, okay, it remains at rest. So this is an example of the application of friction. So now when we look at the free body diagram of the block, what we understand is that there is some kind of a force that the surface is applying on it, okay, or the ground is applying on it, okay, which is able to prevent it from slipping. And in this case, that type of force will be called a static friction. Static because the object is remaining at rest. So apart from the vertical forces, which I'll definitely show, normal reaction and weight, but because the block is not accelerating, something is balancing this external force, and that is acting at the lower surface because of the roughness of the floor below. So in this case, that force friction we generally denote with a small f symbol, and because it is static friction here, we'll denote it with f small s. So this is the free body diagram of the block. To complete it, of course, we need to show the vertical forces also acting on it, which is the normal reaction, okay, and the weight. But because the acceleration of the block is zero, so what is happening? F is getting balanced with this. So Fs is what we call the static frictional force, okay, applied on the block by the rough surface, okay, to prevent it from slipping. Okay. So it's acting in such a way that it is able to prevent it from slipping or sliding along the surface. Okay. So this is an example of what we call static friction. We will see later that there are two types of friction, static friction and kinetic friction. But just first go through this section and make sure you understand everything, including the free body diagram of the block. Okay, let's look at another example to understand a different situation, similar but different in a certain way, situation of the action of friction. Now suppose we are observing something where again there is a block on a rough surface, but this time it is sliding along it because of some external force. However, the relationship between this external force and the observed acceleration is telling us that there is friction acting. So suppose we have a situation where this is a rough surface. Now in this particular example, suppose it is given to us that the mass of the block is equal to 10 kilograms. The force we are applying is 20 newtons, but the acceleration of the block is only 0.5 meters per second square. So what can we conclude from this? So therefore, we can conclude that since the acceleration A is less than F by m, you can see that F by m is 20 divided by 10 or 2 meters per second square. Okay, and the acceleration is only 0.5 meters per second square. So since this is happening, therefore we can see that the net force acting on the block is less than F. Okay, so that tells us that that means friction acts on the block such that it opposes slipping again. Okay. However, the amount of friction acting this time is less than the external force. So that's why the acceleration is not equal to 0. It is not able to balance the external force. Okay. So it acts such that it is opposing slipping. However, friction is not able to prevent slipping because it is not enough to balance the external force F. So this time when we make the free body diagram of the block, what we can see is that this force F is acting on it. There is some friction acting from the ground on it, but this is what we call kinetic friction, okay, because there is some acceleration involved now. So this time what we observe is that F minus kinetic friction is equal to mass into acceleration. So that means that kinetic friction of F minus ma, that is 20 newtons minus 10 into 0.5. So that means kinetic friction of 15 newtons acts on the block. Okay. So this type of friction acting here, it is called kinetic friction. Now I'll give you the proper definition of what is the difference between static friction and kinetic friction. But just make a note of this example first. Note down this example and then Prince, I'll take you back to the previous example once more. First note down this example also. And of course, normal reaction is balancing weight. So that in this case would be 100 newtons. Okay, now next thing we'll understand the difference between the two types of friction. Kinetic friction and static friction. Okay, so what is the definition of kinetic friction versus what is the definition of static friction? So static friction is the type of friction that acts between two surfaces in contact, okay, which are at rest with respect to each other. Okay, and friction acts to balance the external force, okay, which is acting tangentially okay, to create slipping. Whereas kinetic friction is the type of friction that acts when actually slipping is taking place. Okay, so kinetic friction is the type of friction that acts between two surfaces in contact, okay, and slipping with respect to each other. Okay, so kinetic friction acts in such a way that it opposes the slipping. The direction of kinetic friction will always be such that it opposes the slipping. Okay. So as you can see in the previous examples, in the first example, we had a situation where the block was at rest with respect to the ground, but it had a tendency to slip because there was an external force acting on the block horizontally, and but for friction, the block would have slipped. Okay, but why it was not in a state of slipping? Why its velocity was zero and acceleration was zero? Because the static friction was able to balance the external force. So this thing was happening, that it's the static friction acts in such a way that it is able to balance the external force which is acting tangentially to create slipping. Whereas in the second case, we saw that when we apply the external force, okay, in spite of friction being present, it was not able to balance. So the block was accelerating. So there was relative motion happening. Okay, so it opposes the slipping, but there is slipping between the two. There is relative motion with respect to each other. So that is the difference between the two types of frictions or the two categories of frictions, which we call static friction and kinetic friction. Yeah, so see, Prince, in the case of kinetic friction, what is happening is the block is actually moving now with respect to the ground. So what will happen is that while friction is acting, this is only the state of the block initially. After some time, the block will be here. After some time, the block will be here because it's accelerating. But while it is accelerating, the kinetic friction acting on the block is acting in such a way that is trying to oppose the slipping. You understood the point now? Yeah. So with more numerical examples also, we'll understand more about this. Okay. So if the friction is acting in a situation where the surfaces are not moving with respect to each other, they are at rest with respect to each other, then it is called static friction. Whereas if the friction is acting in a situation where there is actual slipping at the point of contact or at the surface of contact, then the type of friction is called kinetic friction, and we generally denote it with the symbol small f subscript k in the free body diagram. This is denoted with the symbol Fs like this. Okay. Now next we'll understand what are the factors on which static and kinetic friction depend. Yeah, we will discuss about that. Okay. Yes, we will discuss about what are the factors on which the amount of static and kinetic friction depend on. Okay. So static and kinetic friction. So to understand static friction better, first let us think of an experiment. So suppose in the experiment, our situation is very similar to the first example that we took, that there is a block of certain mass lying on the ground. So you haven't written down to see, okay. We'll just take a minute and go back to the previous section. You can finish writing this down, then we'll come back to. Yes, this part, Tulsi. Okay. Yeah. So coming back to the factors on which static and kinetic friction depends. So if we are doing an experiment where suppose we have a block of certain mass lying on the ground, and what we do is we are applying an external force on this in such a way that the force is increasing very slowly with time. So we apply a force. This is an external horizontal force which gradually increases with time. Okay. And of course, the surface on which the block is there is a rough surface. Okay. So what we'll observe is, now suppose just to represent this force, I'm showing force as a function of time. And I'm observing that the force is increasing very slowly like this. So with time, the force is increasing. Now what I'll observe, as far as the block is concerned, the block is at rest initially. Okay. The block will not accelerate for some time. The block will initially be at rest, and only at a certain time it will start accelerating like this. So if that time is, let's say, t naught, so on this graph at that time t naught, the value of the external force is some f naught. So interpreting these two, we see that as I'm gradually increasing the force, till the force reaches a certain value f naught, there is no acceleration. So the observation here is that for the magnitude of force being less than equal to f naught, the acceleration of the block is 0. So that means what is happening during this time, static friction acts such that it balances the external force and prevents slipping. Okay. But as you can see from the experiment, this cannot go on forever. If my force goes on increasing, the static friction cannot go on counterbalancing the static friction forever. There's only a certain limit up to which that can happen. So that limit I'm observing is how much? It is this particular value f naught. Okay, we'll do numerical examples also, but let's just think of this as an observational experiment where we are not so concerned with the actual values. We are more concerned with what is happening in terms of the behavior of friction. So very slowly we are increasing the amount of force, and we are observing that till the force reaches a certain limit, we are not able to move the block. We are not able to overcome friction. Okay, so that means static friction is able to counter the external force, or it is able to balance the external force, but only up to a certain limit. Whereas what happens the moment my force, okay, whereas okay, when the external force becomes greater than f naught, what is happening? Static friction is no longer able to balance f, okay, because it cannot exceed a certain limit, and the block starts to slip. So when it starts to slip, what will happen? Kinetic friction will start acting on it. As it slips. Okay. So this is the first thing that we'll observe if we try out an experiment like this. Okay. So what that tells us that static friction has a maximum limit. It cannot go beyond that limit. Okay. Now next we'll discuss what that limit depends on. So note down this part, and the next thing we'll see that what are the factors on which that limiting value or that maximum value of static friction depends on. Okay, so the inference from this part, the inference is that it means that static friction has a maximum possible value up to which it can balance the external force. This value is technically called limiting friction. It's a limit, it's a maximum limit. So we call it the limiting friction. Now, next thing we'll understand what are the factors on which this limiting friction depends. Okay, so hope the point is clear up to this point. Hope the concept is clear up to this point over here. You're understanding the relationship between these two graphs. The motion is not starting till your force exceeds F naught. Okay, so F naught is occurring at time T naught. So that is why your acceleration is 0 up to the time T naught. अभी उसके बाद क्या हो रहा है, we will come to that later. Okay, right now we are concerned with the static friction part. So the static friction part is in which part of the time? In this part of the time, because here the acceleration is 0. In this part of the time you can see the acceleration is 0. So during that time what is happening? This is what is happening. The static friction acts such that it balances the external force and it is able to prevent the slipping. But the moment your external force exceeds a certain limit value, which is F naught over here, we see that this situation cannot happen anymore. Static friction is not able to do its job. It is not able to prevent the block from slipping. So next thing we'll understand is what are the factors on which limiting friction depends. So this limiting static friction the limiting friction value, or what we call the maximum static friction. Okay, the maximum static friction that is available between a surface and a body. So we can give it the symbol like this, Fs maximum. Depends on two things. The normal contact force or the normal reaction force between the two surfaces in contact, okay, which we generally denote with the symbol N. And the second thing is it depends on the material of both the surfaces. Okay, so for example, concrete on concrete will provide more friction compared to wood on concrete. Okay, polished wood on polished stone will provide even lesser amount of friction. So it just doesn't depend on the normal reaction alone. It also depends on what material both the surfaces are made of. Okay, so how that affects, we'll discuss about that next. First, make a note of this point. So it depends on these two factors. Okay, so now let's come to the formula to understand this. So this maximum static friction, or what we call limiting friction, is given by a formula µs into n, where n is the normal reaction, as we discussed earlier, force, whereas µs, it is called coefficient of static friction. Okay, so it is basically a dimensionless or unitless constant. It does not have unit or dimension. This is just a ratio. And typically, it is less than 1. Okay, generally speaking, the coefficient of static friction is less than 1. So the value of this coefficient of friction, this actually depends on the material of the surfaces in contact. Okay, so the value of the coefficient of static friction, that depends on the materials of the surfaces in contact. And it is not something that we can determine by some formula or some theory. It is experimentally determined. So here in this chapter for you in questions, the value of µs will be given to you. Okay, but in technology application and in engineering, we do experiments to measure the coefficient of friction between different materials. Okay, so let's look at an example to understand this. So as I said, we are discussing about static friction first. We will come back to kinetic friction and the factors that kinetic friction depends on. So once again, that same standard situation, we have a horizontal surface on which we have kept this block. But this time some values are given to us. So the block is at rest initially. And this surface has coefficient of static friction given to us as 0.4, whereas the mass of the block is 5 kg. Okay. And we'll take the acceleration due to gravity as 10 meters per second square. So first of all, so this block is at rest initially. Okay. So first of all, find out the minimum magnitude of horizontal pushing force needed to make the body move, or basically slide along the surface. Okay. Secondly, find the magnitude of friction acting on it when a horizontal external force of magnitude, so we'll do this in few parts. The first part, the magnitude of the force that we are applying is 5 newtons. Second part, the magnitude of the force we are applying is 12 newtons. And third part, the magnitude of the force we are applying is 18 newtons is applied on it. Then we'll do a third part also, but first just work out these two parts and tell me the answers. Okay, very good. So first part is correct, Kanishk. Yes, very good, Sitish, that's correct. Yes, Anmol, all 3 parts are correct. Tantresh, all parts are correct. Very good. Okay. So very good. All of you got this correct. So I'll just show the method for everyone here first. So what is happening is, see, we are keeping the block firstly on the surface such that when we are applying some external force, it's only going to be horizontal. So that external force is not going to interfere with the normal reaction. The normal reaction मेरा कितना रहेगा? In spite of applying the horizontal external force F, my normal reaction is going to remain only affected by the weight of the body, which is obviously a fixed value. So मेरा normal reaction हमेशा कितना रहेगा? 50 newtons के बराबर, because M was 5 kg. So it doesn't matter what force I apply, the normal reaction will be equal to the weight, which will be 50 newtons. So what this fact now tells me is that the maximum static friction available to me is this. So that is 0.4 into 50. So that is 20 newtons. So this tells me that the maximum static friction available is 20 newtons. Okay. So therefore, I can see that unless F exceeds 20 newtons, okay, static friction will balance F and the block will remain at rest. Okay, so this really answers all the things. Okay, it answers the first part, that F has to be greater than 20 newtons for the block to move. Even slightly will do. So 20.0000 something one will also do. But so basically it has to be that the limit value is like 20. The moment you're greater than 20, the block will move. Okay. But second part, it tells me, for example, that when the force is equal to 5 newtons, the block will be at rest. The acceleration of the block will be 0 because static friction will act in this way now. So the free body diagram of the block will look like this for this part. Static friction is there such that the block's acceleration is 0. So that means this will be this. So the amount of static friction acting in this case will be 5 newtons. Remember that just because 20 newtons of friction will be available to us, that doesn't mean that 20 newtons will act in this case. You know, when I'm applying a force of only 5 newtons, the friction will not be 20 newtons because that would be ridiculous. Okay, I'm applying a force of 5 newtons forward and the block is accelerating backwards because of 20 newtons of friction. That doesn't happen. The friction will adjust itself to just that much that is required to balance this force F so that the block does not accelerate. Because what is the job of friction, static friction? What it's trying to do? It's trying to prevent slipping. It's not trying to make the block move backwards. It's trying to cut the force F so that the block doesn't slip. So it will apply only 5 newtons of value. When I increase the force from 5 newtons to 12 newtons or whatever, then accordingly static friction will again increase and it will become how much? 12 newtons now. It won't increase to 20, it will just increase to 12. If I again decrease the force to 5 newtons, automatically static friction will decrease itself. So it is like that magical thing that it keeps adjusting itself according to the amount of force that we are applying. Okay. So when this is 18 newtons, the static friction will also be 18 newtons. And again, the acceleration of the block will be 0. Okay, so is this part clear to all of you? Okay. Now the third part of the question. Yes, very good. The third part of the question, we'll see something slightly different happening. Okay. Now in the third part, suppose we apply the force. Okay, second part, Prince. Okay. So see, Prince, in the free body diagram, what I know is कि जब तक मेरा force 20 Newton से ज़्यादा नहीं होगा ना, what is happening? The acceleration of the block will be 0 because static friction is balancing F. This is clear, no, Prince? So that means when I am applying the force of 5 Newtons, what is going to happen? The acceleration of the block is going to be 0, no? So if acceleration is 0, that means net force is 0. So how much is static friction is acting? Exactly 5 Newtons, huh? Because it has to cancel the external force. Is it clear now? So when I'm pushing with 5 Newtons, how much friction will be acting from the floor? Exactly 5 Newtons. Because, yes, that is the thing. Because they go friction, see Prince and Kushal, both of you, what is the job of friction? What it's trying to do? It's trying to prevent slipping. Na? अभी मैंने बाहर से 5 Newtons force लगाया है. So what friction needs to do to prevent slipping? It needs to counter it with a 5 Newton force. Na? So automatically it will apply 5 Newtons. Friction is not equal to mu s into n. is the maximum friction available, which is mu s into n. You're understanding? There's a difference between the two things. One is I'm saying that the friction's value is only mu s into n, but that's not correct. I'm saying that the maximum possible friction I can get, that is 20 newtons. But actually how much friction is acting, that depends on what is trying to make the block slip. Na? If a force of 5 newtons is applied, then how much friction will act to prevent it from slipping? Only 5 newtons, because net force should be 0. Understood, na, Prince? Why the net force? See, it's not slipping. Na? So acceleration 0 करने के लिए condition क्या है? That static friction has to balance F. So that is why if F is 5 newtons, friction is only 5 newtons. When I increase F to 12 newtons, automatically friction increases to 12 newtons. But the point is, if I increase friction, if I increase capital F to 25 newtons, yes. So for no acceleration, the friction will be equal to the amount of external force. But this thing can only happen up to an external force of 20. The moment my external force becomes 22 or 21 or 25 or something, now this will not happen anymore. The acceleration will not remain 0. Okay, very good. Okay, now before we come to the situation of kinetic friction, now let's see another thing that can happen. Okay. So in the third part, if I'm now doing this, the same block lying on the same surface, so same coefficient of friction and all that. Okay. But this time, the external force I'm applying, I'm not going to apply it horizontally. Okay. So the block's mass is still 5 kg. The surface still has a coefficient of static friction of 0.4. Okay, Prince, I'll take you back to the second part, but let's just get working on the third part first. Okay. So this time I'm applying an external force like this. Okay. So now this external force is applied at an angle of theta to the horizontal. So external force F is applied at theta equal to 37 degrees with respect to horizontal. This time this is what is happening. Okay. And again take G as 10 meters per second square. So find the minimum magnitude to make it move again. Find the minimum magnitude of F to move the block in this situation, that I'm applying the F not horizontally but at an angle of 37 degrees to the horizontal. Okay, so just try this out, people. So the hint to use this time, when you make the free body diagram, your normal reaction is not going to be equal to weight. Just try and understand why that's happening. But the normal reaction will not be equal to the weight. It will be different because F has a vertical component. So that is where your whole free body diagram, resolution of vectors and all that becomes important again. 125 by 14, Kanishk. Okay. So I'll just verify the result. Okay. So let's make the free body diagram. So for this situation now, on this block, I'm applying the external force at an angle of 37 degrees. Okay. mg is there, m is 5 kg given to me. Normal reaction is acting vertically and static friction will act horizontally, assuming it does not slip. Okay. Assuming acceleration is 0. So static friction is acting. So for that situation now you can see that n plus f sine 37 is equal to mg. This is your vertical equation. Okay. And along your horizontal, what is happening is that f cos 37 is balancing static friction. That is your second equation. Okay. So this one is telling us that n plus 3 by 5 f is equal to 50. Okay. Or in other words, n is equal to 50 minus 3 by 5 f. This is what I am getting from equation 1. And from equation 2, I am getting that static friction is equal to 4 by 5 f. Okay. Now I'll apply the limiting condition. Okay. So what is the maximum static friction available? Mu m. Okay. So therefore, for slipping to occur, this force that I'm applying, 4 by 5 f, that should become greater than the maximum static friction available. The moment this becomes greater than the maximum friction available, slipping will occur. So the block will move for slipping or motion. So I'll apply that condition now. So 4 by 5 f should be greater than mu s into n. Okay. So 4 by 5 f should be greater than, now mu s was 0.4 and normal reaction from here, मैं substitute कर दूंगा 50 minus 3 by 5 f. So now I'll get this kind of an equation. So take f on one side. So you have 4 by 5 plus 0.4 into 3. So that is 1.2 by 5 should be greater than 0.4 into 50. Okay. So all I have done in this equation is taken the terms of capital F on the left hand side and kept the constant, that is 0.4 into 50 on the right hand side. Okay. So ये कितना हो जा रहा है? F into 5.2 by 5 should be greater than 20. So that means F should be greater than 20 into 5 divided by 5.2. So F should be greater than 100 divided by 5.2. So it's not going to be very different from the first answer, but not exactly the same also. 19.2. This is the condition we are getting. Okay, so just go over the mathematics part a little carefully once, because the free body diagram part is very simple. If you want, you resolve it and show it in a separate free body diagram. So you have F sine 37 acting like this, F cos 37 acting like this. So F cos 37 कोई friction balance करने की कोशिश कर रहा है ना? So that is why we have this condition for no slipping. But if we want to make it slip, then this has to happen. This thing has to happen. Okay, so hope this part is clear to all of you. Okay, finish writing this down. Okay, finished, Prince. Oh. Okay, now let's come to kinetic friction. Let's understand the properties of kinetic friction. So as we have seen, kinetic friction acts when there is slipping. That is when there is relative motion of the two surfaces in contact tangentially. That means along the surface of contact. Okay. Now the most important thing, the magnitude of kinetic friction does not depend on external force. Okay. The value of kinetic friction is equal to, the magnitude of kinetic friction is equal to another coefficient multiplied by normal reaction. So what this means is that the same magnitude of kinetic friction will act no matter how much the external force. Okay, as long as there is slipping. So I'll explain this with different situations and you will understand the meaning of this properly. Now this coefficient of friction again depends on the materials. So this coefficient of kinetic friction again depends on the material of the surfaces in contact. The value of mu k is mostly either equal to or slightly less than the value of mu s. So whatever value of coefficient of static friction between two materials, typically the value of kinetic friction coefficient mu k will either be exactly the same or it will be slightly less. Now the tendency to be slightly less is because when there is slipping occurring, the same two surfaces cannot grip each other as well as when they are at rest. So that is why once slipping starts, the friction available reduces a little bit, and that's why the kinetic friction coefficient typically mu k is slightly less than the value of mu s. Though in many cases it can be negligible, the difference can be negligible. So we can say that more or less the value of mu k is equal to the value of mu s, or the coefficient of kinetic friction equals the coefficient of static friction. Yeah, I'll explain the notes here. So see, typically what happens is that suppose we know that some kind of brick on let's say tar. On a tar surface, if we have brick, suppose the coefficient of static friction is 0.6, then typically the coefficient of kinetic friction will be something like this 0.60, this will be 0.56 or 0.55 or something like that, or may even be 0.6. So always the kinetic, so between the same two surfaces, जो भी मेरा μs का वैल्यू है, my μk will either be exactly the same or slightly less. It will never be the other way around, that μk is more and μs is less. Okay, and what the value is, there is no theoretical way of determining this. We actually have to do an experiment to determine the coefficient of static friction separately, and again do a separate experiment to measure the coefficient of kinetic friction. So that's why in questions you will always be given the values of coefficient of friction as a data. Okay, and in certain questions what might happen is, instead of μk and μs, only some value of mu is given. So if mu is only given, that means that the value of kinetic and static friction have the same value. Brick, brick, BRIC capital, ETA. Okay, so brick is basically baked clay. So in a sense it is baked clay. And yeah, again Prince, that depends on the nature of the surface. So here anyway we are doing questions theoretically, so we won't really worry too much about that. For some materials it's noticeable, the difference, whereas for some materials the difference is negligible. But in general, as I said, it will either be equal to or slightly less. It won't be a huge difference. Like, kinetic friction's coefficient will not be half of static friction's coefficient or something like that. There won't be a 50% or a 20% difference. It will be a very small difference. So that is just the nature of materials, how they work. You can of course research on this point yourself. There is a lot of stuff in reference books and in the internet about coefficient of friction and different type of experiments, and but for our purpose this is what we need to know, because ultimately we have to use the values in solving numerical problems of mechanics. Okay, now let's come to an example to understand this better. So same this thing, I'll take same values which I had taken earlier, or rather same kind of situation. So this time I have a block which is of mass 10 kgs. Okay. Again, we'll take g as 10 meters per second square. Now it is on a surface which has both the coefficients given to us. Mu s equal to, let us say, 0.3 this time, or 0.30, and mu k equal to 0.25. मतलब typically इतना ज़्यादा difference नहीं होता है. It is more like 0.28 and 0.30, but I'm just taking a theoretical value where one is 0.30, the other is 0.25. Okay, and now the block is initially at rest. So we have to find the magnitude of friction whether it is static or kinetic. Okay, and the acceleration of the block if a horizontal force F is applied. Okay, in a situation where F is equal to, let us say, 15 newtons, F is equal to 25 newtons, F is equal to 35 newtons. So just imagine the block is at rest, and at some time t equal to 0, we start pushing it with a continuous horizontal force. But in one case, we are applying a force of 15 newtons. Whereas in a separate experiment, we are applying a force of 25 newtons. Each time the block was at rest initially. Okay? Each time the block was at rest initially, and we applied a force of these many newtons. So first tell me how much will be the acceleration in the first two cases and the third case. Then we can come to the amount of friction acting. It's very similar to the previous question we did. Only now the coefficient of kinetic friction is also given. Very good. That's correct, Kanishk. So the third case, you are overcoming the static friction and the block starts to slide. So the moment it starts to slide, what kind of friction acts? Kinetic friction. So which value of coefficient you'll use? Mu k. And for example, even if I used a different value of force, yes, Anmol, that's correct. Very good. Even if I used a different value of force like 45 newtons, the acceleration will change, but the amount of friction acting will be the same because it's kinetic friction. Kinetic friction does not change according to the external force. Once the sliding starts, the amount of friction acting will be the same. Nay, Prince, be careful. No. See, when the block is not slipping, what is happening? The net force should be zero now on it. Yes, correct, Anmol. D part is correct. So, Prince, be careful about the first part. Okay. Maximum friction available is 30 newtons. But does that mean that when I apply 15 Newton force, 30 newtons of friction will act? What happened? Exactly. So how much will be the friction in the first case? So see, first thing you understand here is that because again I'm applying the external force horizontally, it does not interfere with normal reaction. So again, it's a case where normal reaction is equal to weight. So that in this case is 100 newtons. Okay. So my maximum static friction available is going to be mu s into n. So that is going to be 30 newtons. So from this, what we can understand that for F less than equal to 30 newtons, what will happen? The acceleration of the block will be zero and static friction will balance the external force. Whereas the moment I apply a force of greater than 30 newtons, the acceleration of the block will not be zero and kinetic friction equal to mu k into n will act. How it will act? Opposite the acceleration. It will try to prevent the slipping. Okay, so that is why in A part, B part, and C part, this is what will happen. Sorry, A part and B part, this is what will happen. When I apply a force of 15 newtons, I know that the acceleration will be zero and the static friction will balance F. So static friction of 15 newtons acts and acceleration is zero. B part I know when I apply the force of 25 newtons, again acceleration will be zero and static friction equal to 25 Newton acts. Okay. But C and D now you can see that it's going to be this case. So for C and D, my free body diagram will change. I mean, it will change in the sense that the situation of the block will change. So I'm now applying a force of 35 Newtons. So I can see that I cannot overcome slipping. I mean, I cannot, the friction is not able to overcome. So this will be kinetic friction. Okay. So now for the C part, F minus kinetic friction will be equal to mass into acceleration. So F minus mu k into n will be equal to mass into acceleration. So 35 newtons. So this kinetic friction is 0.25 into 100 or 25 newtons. So whenever slipping is occurring, 25 newtons of friction will act. So 35 newtons here is the external force minus 25 newtons of friction will provide 10 kgs of mass with acceleration of 1 meter per second square. Okay. And the friction acting will be 25 newtons. Remember, the value of kinetic friction will not depend on how much force we are applying. It just depend on the coefficient of kinetic friction. Whereas the value of static friction, that is dictated by how much force we are applying. Yes, for 30 Newton also it will be 0. Even if we apply a force up to 30 Newtons, if we applied F equal to 30 Newtons with the block initially at rest, okay, initially at rest, okay, the static friction of 30 Newtons will act and the acceleration will be 0. Only when the force becomes greater than 30 Newtons, even by a very little amount, then it will start slipping. And when it starts slipping, the friction for 31 Newtons, yes, if we apply 31 Newtons, then the friction acting will become 25 Newtons. Because it started slipping, no, unknown. So the moment it starts slipping, the friction changes from static to kinetic. So it will become mu k into n. So whether we are applying 35 Newtons or 31 Newtons or 30.001 Newtons also, the friction will change to 25 Newtons. It will be kinetic friction. Because once it starts slipping, the surface cannot grip as well. No? So the coefficient of friction reduces. Okay. Is the point clear, Anmol and Prince both? Okay. So the moment I apply a force greater than 30 Newtons, it doesn't matter whether it's 30.1 or it's 31 or it's 300. Okay, kuch bhi ho. The acceleration of the block becomes non-zero and the friction acting becomes kinetic friction, so it becomes 25 Newtons. That is the behavior that we observe in case of rough surfaces. So that's why in the D part, when I increase this force to 45 Newtons instead of 35 Newtons, it doesn't make any difference to kinetic friction. The kinetic friction acting will still be the same amount, mu k into n. So it will be 25 Newtons. So, but the acceleration will change, of course, because the net force is changing. So F minus kinetic friction is ma. So this time this becomes 45 minus 25 is 10a. So the acceleration increases to 2 meters per second square. Yes, that's correct. Yes. Okay. Okay. So hope the values are clear to all of you here. Okay. Now let's come to a really interesting situation, which will teach you more about the behavior of static and kinetic friction. Okay. अभी suppose same example है मेरा. Mass of the block was 10 kg. Okay. The coefficient of static friction was 0.3 and the coefficient of kinetic friction was 0.25, and initially the block is at rest. So now what happens at t equal to 0, a horizontal force of, let us say, 35 newtons starts acting continuously. Okay. So it's like, a constant horizontal force. I'm not varying the amount of force I'm applying. I'm continuously pushing it with 35 newtons, and at t equal to 10 seconds, F is withdrawn. So it stops acting. Okay. So make the FPD of the block, okay, and show its acceleration or deceleration, as will be the case for any time between 0 and 10 seconds. Okay. And then again for any time after 10 seconds. Okay. And determine the total time for which the block moves. Okay. And the total displacement. So one FBD you already know. It's the same as the third part of the last question that we've done. But now you have to think carefully what will happen when we withdraw the external force. So think a little bit in terms of kinematics also. You know the value of acceleration and you know the body started from rest. So you know what's happening between 0 and 10 seconds in terms of kinematics also. It has a constant acceleration because F is constant. Yes, very good. That is correct, Anmol. Correct, Kshitij. Okay. I will just check the displacement value that you got, but mostly it seems to be correct. Okay, so first of all, let us understand the acceleration and the deceleration later, and why that happens. So let's trace the motion right from the beginning. The block was at rest, okay, but we started pushing it with an external force of 35 newtons, okay, and because this force exceeded the maximum friction available, so the block will start accelerating. We know this, okay, and the friction acting on it will be kinetic friction. Okay, so we know that F minus kinetic friction will be mass into acceleration. This we've already done. So 35 minus 25 will be equal to 10a. So it has a positive acceleration of 10 meters per second square. So this process, it continues. It continues all the way. Okay, so at some time now, in between 10 seconds, also this process is continuing. So by now it has a velocity which is equal to a into t, because it's having that acceleration continued, because I'm continuously applying this force. Okay. Kinetic friction is equal to mu m, like this, mu k into m. Okay. But now the interesting thing happens exactly at t equal to 10 seconds. Now this force stops acting. But by the time I reach there, it's already got some large value of velocity. No? So let's say it's got some velocity v1. Okay, so let's find out first of all. And it's also got some displacement from here to here of S1, let's say. Okay. So we can see that from t equal to 0 to t equal to 10 seconds, it has an acceleration of 1 meter per second square. So the displacement will become half at square. So half into 1 into 10 square. So that is 50 meters. Okay. And the velocity, which I have labeled as v1, at that time will become 10 into 1, or 10 meters per second. So at this moment it's doing like this. Okay. But the moment I have withdrawn the external force, अभी क्या हो रहा है, ऐसा friction act कर रहा है. So for any time greater than 10 seconds, till it comes to rest, what is happening is it will have a deceleration. So let's say that deceleration is a prime because of friction. So t greater than 10 seconds, what is happening? This kinetic friction acting on it. So now you can understand what I'm saying, that kinetic friction does not depend on external force. यहाँ पे external force लग रहा था तो kinetic friction कितना था, mu k into n. Now kinetic friction has stopped acting. Sorry, external force has stopped acting. Capital F is not there. So you might ask, why is friction acting? It's very simple. Why is friction acting? Because the object is slipping. It is in a state of motion. It's sliding on the surface. So as long as it is sliding, kinetic friction will act. And what will be the direction of kinetic friction? It will oppose the slipping. So the slipping is happening along the positive x direction. So kinetic friction will continue to act till what will happen? Till the block comes to rest. At some stage over here, once the block comes to rest, now friction stops acting. Now finally, friction will stop acting. So it will remain at rest. So we need to find out how much time that is, and we need to find out how much displacement that is. So for the second part, you can see kinetic friction is equal to mass into deceleration. It's acting in the backward direction. So mu k into normal reaction is mass into deceleration. So 25 newtons is equal to 10 a prime. So the rate of deceleration is equal to 2.5 meters per second square. So the way to answer the question will be that there is an acceleration of 1 meters per second square from 0 to 10 seconds. Okay. And thereafter, and after 10 seconds, there is deceleration of 2.5 meters per second square till it stops. So we need to find out when it stops. And for that, again, you have kinematics, which is very easy. Yes, that's correct, Beta. Anmol, that's correct. Okay. So first things first, make sure all of you are clear with the two different free body diagrams. This free body diagram, which is there when F was acting, and this free body diagram when F stops acting, but the body is still slipping. Okay. So let us say that it stops at t equal to 10 plus delta t seconds. It stops. Okay. So V1 was equal to how much now? It was 10 meters per second at t equal to 10 seconds, and V is 0 at t equal to 10 plus delta t seconds. So this V should be equal to V1 minus A prime delta t. So 0 should be equal to 10 minus 2.5 delta t. So delta t is coming out to be how much? 4 seconds. Yeah, so Prince, what is happening now? I have pushed it for 10 seconds with this force. So by the time you come to the 10 second, it's developed a velocity of how much? It's developed a velocity of 10 meters per second. This, and then I stop pushing it. Okay, so once I stop pushing it, what happens? It starts decelerating because of friction. It's sliding on the surface now. So as long as it's sliding, friction will prevent this. Will oppose the sliding or oppose the slipping. So friction continues to act backwards, but now there is no forward force now. So instead of accelerating, now it starts decelerating. So you think of this free body diagram. What is the result for this? Net force is equal to mass into acceleration. So net force is also backwards. So A prime is also backwards. So it is a deceleration of this much. Is it clear now? Okay. So अभी deceleration कितना है? 2.5 meters per second square का है, और 10 seconds पे उसका velocity कितना था? 10 meters per second. So कितनी देर बाद जाके stop हो जाएगा? V will become 0 when the time is 10 divided by 2.5 or 4 seconds. Okay, but 4 seconds from this instant. So on my clock, the time will be how much? 10 plus 4, 14 seconds. Now the total time will be 14 seconds. So delta t is the time beyond 10 seconds. So that's why I've written the time like this, that at some time 10 plus delta t, it stops. So when it stops, what happens? Its velocity should be 0. So you can see that 10 minus 2.5 delta t should be 0. That means this is 4 seconds. So it takes 4 seconds for it to decelerate and stop. Okay, so that means the total time of motion for the block from starting to end is how much? It is 14 seconds. For 10 seconds, it accelerates. Okay, and for 4 seconds thereafter, it decelerates. Okay, and now we'll find the total displacement also. We'll find the second part of displacement, S2. Okay, and the net displacement will become S1 plus S2. So you'll see that the net displacement should become 70 meters, because your S1 was, in my diagram, this S1 is 50 meters. Okay, so now what is the easiest way of finding this S2? To find S2, you can see that we can take the initial velocity as V1, which is 10 meters per second. The final velocity is 0, and the acceleration as minus A prime, or minus 2.5 meters per second square. We can use the relation that V square is equal to U square plus 2AS. So 0 is equal to 10 square minus 2 into 2.5 S2. So S2 will come out to be how much? 100 by 5, or 20 meters. Okay. That's why the total displacement will be equal to S1 plus S2. So that is going to be 70 meters. But out of the 70 meters, for the first 50 meters, the block was accelerating. That's happening in the first 10 seconds. And the next 20 meters, the block is decelerating, and that's happening in a space of 4 seconds. So another way to interpret this result is that you just visualize the velocity time graph of the body or of the block. Okay. The velocity time graph will look like this. It will initially accelerate at a comparatively slower rate, 1 meter per second square, and then later decelerate very sharply in comparison at 2.5. So in 10 seconds, it's achieving a maximum velocity of 10 meters per second at an acceleration of 1 meter per second square. Then it starts decelerating at 2.5 meters per second square. But this is a negative acceleration or a deceleration. Okay, and it achieves 0 at 14. So the total displacement is actually the area under this graph. So this area is the total displacement. So that also you can check out, that will be 70 meters. Half base into height करके निकालो. That's another easy way of finding the net displacement. Okay, people, so hope this is clear. So this is where we'll conclude today's session. So next time we'll be discussing about more interesting situations with friction. For example, friction on an inclined surface. We have discussed about friction on a horizontal surface. Yeah, Prince, I'll share the file again with you. Okay. But in the meantime, please finish up questions from Newton's laws of motion, especially H.C. Verma. If anything is pending, try to finish it up and send me any doubts if you have. Also, you can start doing questions from the module exercises, okay, particularly exercise 1. There are a lot of questions with friction and few questions without friction. So especially the questions without friction, you can start working on them and complete them. And also, if you read up about the theory part a little more, it will help. So the chapter of friction from either H.C. Verma or Resnick Halliday, if you read up a little bit ahead, again, it will help us in understanding the next couple of lectures. Okay. So that's it for today, people. Wish you all the best.